Welcome back, everyone, to this explainer by Forge College. So in our last lesson, we were way up in the clouds, right? We were analyzing Solana architecture for the report, dealing with some highly theoretical concepts. Today, we're coming right back down to earth. We're transitioning from that abstract world of decentralized networks into the gritty, noisy, and honestly, very physical reality of Bitcoin mining. We're going to be looking at the actual metal, the electricity, and the thermodynamics that make this whole system tick. So let's just dive right into it. Okay, here's our blueprint for today. We'll start with building the site, look at the delivery fleet, move into managing energy, and finally we'll connect it all back to network stability. You know, there's a really wonderful irony here. We spend all this time talking about a purely digital currency, yet it relies entirely on very gritty physical things. It's a stark contrast. On one hand, you've got this clean economic math, hashes, reward schedules, all that. But on the other hand, you've got this messy operational reality of immense heat, stressed power grids, and broken cooling fans. The beautiful math literally only works if the machines don't melt. All that economic calculus you've learned, it depends entirely on these physical, tangible inputs. Section 1, building the mining site, the physical foundations. So, site selection isn't just some administrative checklist you tick off. It is the literal foundation of your profitability. You're facing a barrage of real-world constraints before you can even plug in a single machine. We're talking available power capacity, demand charges, cooling capabilities, network connectivity, and of course, local regulations. I mean, you could have the most highly optimized mining rig on the planet, but a bad ping to the mining pool, that's basically the Web3 equivalent of hitting every single red light on your way to work. It can completely tank your profitability for the month. Every physical input is a very real line item on your balance sheets. And listen, nothing requires more active management than heat. When it comes to thermodynamics, you generally have two choices. First is standard air cooling. It's simpler, sure, but man, it is incredibly noisy. Seriously, it sounds a bit like a jet engine taking off in your living room. Alternatively, there's immersion cooling. This is where machines are literally submerged in a non-conductive fluid. It's super quiet and gives you really high efficiency, but it brings some incredibly complex maintenance. So why does this matter? Well, dropping the inlet temperature of your machines directly impacts ASIC efficiency. A cooler machine just calculates more efficiently, but an immersion setup, that drastically alters your baseline fixed costs. You always have to weigh that immediate capital expense against the long-term thermodynamic gains. Moving on to Section 2, the delivery fleet or ASIC hardware. I absolutely love this mental model from our source material, treat ASICs like delivery trucks. Hash rate is cargo, power is fuel, and uptime is road availability. It's brilliant, right? It makes all these abstract hardware metrics instantly relatable. Instead of getting bogged down in watts and terahashes right out of the gate, just picture your mining machines as a massive fleet of commercial trucks. You want maximum cargo delivered using the minimum amount of fuel, and you absolutely need those trucks out on the road, not sitting in a repair shop. And that truck metaphor leads us perfectly into the concept of effective hash rate. Basically, this is the cumulative, uptime-adjusted efficiency of your hardware over time. Look, vendors will always try to sell you a machine based on its peak sticker specs. It's like a truck salesman telling you a vehicle can hit 120 miles per hour. But if that incredibly fast truck is constantly in the mechanic shop, it's going to deliver way less cargo over the course of a year than a slightly slower, but much more reliable truck. Effective hash rate calculates what you actually delivered, factoring in the operating history and the inevitable failures. And make no mistake, failures are inevitable, mainly because of relentless wear and tear. These machines are running flat out, 24/7. They suffer from thermal cycling wear, so heating up and cooling down over and over, as well as constant voltage stress. Parts are going to break. Power supply units will fail. Because of this, lowering your MTTR, that's your mean time to repair, is absolutely critical. If you don't have spare parts on hand, a simple broken fan suddenly turns into days of zero cargo delivered. And just like that, your effective hash rate plummets. All right, Section 3, managing energy or fueling the fleet. And by the way, if you're enjoying this, exploring courses at Forge College is a great way to dive even deeper into Web3 mechanics. But back to energy. Energy is by far a miner's largest recurring cost. To manage it, successful operators usually follow a step-by-step workflow. First, they assess supply. You really have to understand your grid tariffs and industrial rates. Second, design distribution, planning out the electrical infrastructure right down to the submeters on the server racks. Third is active load management. This means having a control layer so you can actually throttle machines during peak price events. And fourth, monitor and log. You need to collect granular telemetry on power, temperature, and fan speeds. This exact workflow is how successful operators maintain their profit margins, even when energy pricing and physical conditions are just shifting wildly all around them. Let's look at how these operational issues actually connect to real-world mitigations and trade-offs. Take high demand charges, for example. If energy gets wildly expensive for just 1 hour, your mitigation is staged load shedding. The trade-off? Well, you lose instantaneous revenue, but you save massive amounts on your monthly power bill. Or think about a cooling system failure. If a fan breaks, you use automated controls to lower that specific machine's power. It all comes back to telemetry. Having those submeters on your racks allows you to convert raw electrical tariff data into smart, automated control signals. It is an incredible balancing act. And that actually brings us to one of the most fascinating concepts in mining: derating. Derating is intentionally running machines below their maximum capacity to reduce heat and extend the hardware's lifespan. Now, I know that sounds completely counterintuitive, right? Why on earth would you purposefully slow down a machine that is specifically designed to hash as fast as possible? Well, because sometimes slowing the machine down by just 10% reduces its operating temperature just enough to stop it from breaking down. It's actually the smartest way to maximize the lifetime cumulative output of your delivery truck. So we've talked a lot about the physical site, the trucks and the fuel, but let's zoom out for a second and ask a really vital question. How do local cooling and power choices actually affect the global network? Like, how does a single broken fan in a warehouse in Texas impact a decentralized ledger worldwide? Section 4, Operations Meet Network Stability. The key here is that widespread intelligent derating prevents correlated stoppages and stabilizes network block discovery. Think about it for a second. If thousands of miners are all just running blindly at maximum capacity, and a massive heat wave hits the grid, they might all fail or be forced offline at the exact same moment. That takes huge chunks of the global hash rate offline instantly, which makes block discovery completely chaotic. But if local sites have robust infrastructure, active load management, and they intelligently derate their machines, they can weather that storm. Basically, good local operations prevent sudden, localized grid issues from spiraling into a global network crisis. Okay, as we wrap up, here is your capstone prep for the upcoming Mapping the White Paper summary. First, note the real-world site selection trade-offs. Really understand how power, cooling, and tariffs totally dictate success. And secondly, ensure you understand effective fleet efficiency. Remember, it's uptime and degradation that actually matter, not just the glossy vendor spec sheet. Mining really is an economic, engineering, and operational challenge all rolled into one. I want to leave you with this final, provocative thought. If physical constraints dictate digital security, who really controls the network? It's a pretty fascinating question to ponder. Ultimately, the digital realm is only as secure as the physical infrastructure it rests upon. Anyway, thank you so much for joining me for this explainer. To learn more about this subject and explore other incredible Web3 topics, be sure to visit forge.college. Keep exploring, and I'll catch you in the next one.